All right, so this question's all about prime numbers. And it's called Prime Sieve. And if you're like me and you're really uncultured, you're learning that this is first pronounced like sieve, not sieve. And a sieve is something that's used in cooking to basically filter out larger items. So like a strainer or something like that, but for solids. But that's unrelated. So this whole question is, given a number n, an integer, design a function that returns every prime number from up to that number. So say this n was 11 primes. Say this n was 11, we want to return 2, 3, 5, 7, and 11. And in case it's been a while, 0 is not a prime, 1 is not a prime, but every number that higher than that can be a prime. Potentially. So, how would you go about solving this? So, if you were to just do it in your head, you would say, okay, like for example, you would say, okay, 11, that's prime. And you'd say, why? Well, because it's not divisible by any other numbers. What you really did in your head was, you probably said it wasn't even. And you probably did some quick maths like, 3, 5, we've already hit halfway to 11, so we're probably good. So that is the brute force approach. You would iterate through every number from starting at 2, going up to whatever n is. We call that integer as we go up, just I. And we would, so our first iteration would just go to 2. And we would want to take the value up to, we'd basically test every prime up to that number to see, we would just need to see if 2 is a prime. So if something is a prime, we'll call this next value j, and that's going to go from 2 to I. This doesn't make sense for the first iteration, but say we're going through and we're looking at 5. So, I equals 5. We would need to check if 2, 3, 4, we would need to divide all those into this number to check whether 5 was prime. So that would just be a if I mod j equals 0, then we know that it's not prime. Because we're not going up to the actual value. Let's see, this should probably be, ignore the strictly less than or other less than, ignore that for now. But essentially we would go through and we would check, okay, 2, can it be divided by any prime? No, that is prime. 3, does 2 divide into it? No, okay, it's prime. 4, I guess we would go to 4 and we'd say, okay, does 2 divide into it? Yes, not a prime, and so on. So this is actually O of n squared runtime, which is not great for this problem. And it does run in O of 1 space. And you might say, hey, what about the result array? And really, we need to make the result array no matter what. So I would actually call that in place being our solution. So this, I'll call this the brute force. Solution. And you can actually improve it if you take the fact that, remember when I said earlier, okay, that mental math of trying to figure out whether whether 11 is prime, that divide by 2, if you know if you get to like half, so if you're looking at it and you know you get to 6, that's more than half. So you really only have to go to 6. Let's do another couple examples. Let's say 9 and 12. You have to check 1, 2, and 3 for 9, and nothing more. And why is that? Well, what divides into 9? 1 and 9, 3, 3, and 9 and 1. And then for 12, it's 1 and 12, 2 and 6, 3 and 4, and so on. And as you start to look to it, all these sets contain at least one number that is less than the square root. So basically we only have to check from up to the square root of n. So that makes our small search, instead of being an O of n operation, it makes a O of root n operation. And so our runtime actually we can optimize to O of n to the 3 halves, which is better. It's a good trick. Your interviewer will probably ask for better though, and that's where you should get into the sieve. So we're making a mistake by computing this every single time. If they're going to make us compute a whole list, we might as well, as we do the work for 2 and 3 and 5 and so on, we might as well be able to reuse that work and look up that work for pretty quickly. So if we were given n equals 11, say we were able to keep an index of size 12, but really these would be the indices. I guess this would be index 11. And these would just represent the numbers, 0 through 11. 2, 3, 4, 5, 6, 10, 11. We'll call this the is prime array. And everything will start out true, all values. And as we go through, we can just look forward. So if I asked you if 10 is a prime number, you would say no. And I'd say why? And you say because it's even. And I would say, okay, why are even numbers not prime? And you would say because 2 divides into all of them. So you kind of already sieved it yourself. If we know that, so say we're going through, we say, okay, this is not prime, this is not prime. Say we go to 2, 2 is prime, but we know every multiple of 2 up to n is not prime. So this would be true, but 4, 6, 8, and 10, we would do that work there. So when you started looking at 3, and you also determined it was prime, not that that matters right now, but you would say, okay, whatever multiple but 3, 6, 9, and 11, those are not primes either. And as you went through, you could dump the actual prime into the results array while also being able to check quicker whether something was prime or not. How would that kind of look like? Well, you'd still have an array. Well, you'd still be going through every single value. So I'll say this is 0 through n. You would check and you'd say, okay, if you first need to check even if, so like say we're going through and we get to 6 and we know it's not a prime, that's where we should just check that. So I'll just say check is prime. And if it is prime, sieve. Sorry, I did it. It's sieve. Okay. And then just go through your array, and then also if it's prime, add to result. So the algorithm is pretty simple. As for the runtime, it's not very intuitive, but if you said something like it was a recurrence relation of, for that first iteration, you're going to be doing half the array because you're saying 2, 4, 6, 8, and so on. And the next one you're doing a third of the array because you're doing 3, 6, 9. And 5, and really every prime, and then it would be n over 11. Because the 3 would imply you'd already done 9. So you wouldn't have to prove, or you could, for extra bonus points, you could prove in an interview that that was, if you do it, it's actually O of log, or it's O of n log of n. But you could just say off the bat, hey, I know that's better than this. N log n is better than this, so n log of log n is already better than that. And then, so that's run. And then for space, we are using O of n extra space. Before we get to optimizing, there's a couple more, or before we get to coding, there's a couple more optimizations we can make. Let me grab my notes just because I'm blanking. Oh yeah, so actually they weren't on my notes. I have to remember it. Okay. One of them had to do with only checking. So we did the square root check. Another one would be not even having to store the evens. So if we know that in this array that 0, 1, 2, we already know those states, right? But if we didn't have to keep track of any of the even values in the array, we could store it in O of n over 2 space. And how would we do that? So the first item in the array would have to map to the third index. The first one would be to the fifth index, second to the seventh. And really this is just a 2 times, call this I, 2i plus 3. I'll call this j. And conversely, I equals I, let's see, divided by 2, j over 2 minus 3. So if we use this formula to interconvert, we can actually use a smaller lookup table. So that's pretty neat. One more thing. So we were checking from, so when we would sieve something, we would check, say for 3, we would go from, so we would check 3, and then we would start from 2 times whatever the value is. So we'd go to the next one, right? So if we were checking 3, we would go 6, and then 9, and hit the end. But one cool little math trick is that we never actually have to check anything until the square. So if we're checking 3, we can actually start the next one at 3 squared, which is 9, as our first one we check next, because this 6 has already always been hit by a previous sieve. And you can check that with different things. So, and I could do the math if I wasn't 4:17 in the morning, but essentially the next thing you can start at I squared. And that gives us slightly better runtime. I don't think it's a small optimization, but it doesn't actually improve our runtime. Another thing you could note, this is out of order, but as for this runtime here, if you're, as for this runtime here, no, sorry. You could note that many of these would be, never mind. You know what? Never mind. So that's brute force and that's sieving. Let me see if I can pull out, if I can put this into code. So we need our list of results. Or list of, I'm way too tired. Integer results equals new array list. And then return results. And just to be clear, we're going to use our optimizations. I'm going to make this a little bigger, and then I'm going to say, I know it's a to-do, but I just want to make it clear. Our optimizations are our output to space. Actually, I'm going to add these in after. So for okay. So if let's see here. We need to initialize our array right here, right? So we'll just call that a list of integer primes equals, or I guess it's booleans. It'll be a new array list, and we need to set them all to true, if you remember. And in Java, they're all set to false by default, so we need to fix that. Collections dot end copies is really clutch. Let's see, how big do we want it? We want n+1 of them. That's our size of the array list, and then we all want them to be true. This saves these little things. They're nice when they save like a for loop. So we make our primes, and then we should also set primes dot set at 0 to be false. And the same for 1. And then we just need to go through int I equals, let's see here, we're going from 2 through 2, let's see, int I equals 2, I is less than or equal to n I plus plus. So we are doing evens in this, but we do need to check whether n is prime as well. And what are we doing? So if is prime. So if basically if a number is prime, so primes dot get at I, what do we say? If a number is prime, sieve, and then also add to the result. So I'll add it to the result first. Add primes dot get. Let's see. Now it will be I. And then for is j equals I, j is less than. I guess that will be less than or equal to n. J plus equals I. And then we'll just say is prime, or primes dot set at j to be false. So that's bare bones before the optimizations. O of one extra space, or O of n extra space, O of n log n runtime. Running the test code, we can see it all passes. Cool. Let's optimize for, let's do the one for searching from I squared first, because that one's a little simpler, I think. So I guess that would just be here. Really, we can just start from I squared, or yeah, I times I. And that, I believe that should work. No, we got an index out of bounds. Oh, so yeah, on a whiteboard this wouldn't show up, but we're starting to deal with big numbers. Even though we only had, so yeah, that was on test case 22 of 24, probably made specifically to test this. So let's use long here. I times I. Let's use longs for all of these. Let's say convert this to an int here, and that should work. Same test case. Where is it failing? Line 25. Primes on set. Still overflowing because of these guys. I have to make this a long as well. Int. Okay, so if you realize that in an interview, that would be extra points. Okay, so that's the optimization starting to search from I squared. Let's add the one for n over 2 space. Okay, so what did we say we were going to do with the n over 2 space? Well, we knew that 0, 1, and 2 were all pre-computed, right? So right off the bat, if n is less than, let's see here, if n is less than 2, we just want to return a new array list because that's going to mess up what we're going to do. And then we'll make our results array, and then we know that 2 it is a prime. So we'll just huck that in there. And so let's see here, and primes dot set at 2 to be true. Because this array is actually going here, it's always starting from 2, so I and j are going to be at least 2 all the time. And we never check primes. I think we can get rid of these. I don't think we should add it here. I think we should just set it in the primes. Okay, that passes. So we're still good. How do we use n over 2 space? So what is the size of our array going to be? It's going to be a little less than n over 2. Final int size, let's see here. What do we calculate it to be? Let's see, I want to convert, so 0.5 times j. J was n plus 3, or minus 3. No, it was 0.5 times. I've gotta use lots of parentheses here. This was wrong. It's technically this. Ugh, I'm 428. You know, different type of Blake. And then we would want it to be 1 bigger than that. And also make sure this is an int. Okay, and what is this size? This is the size of our array. So this remains the same. So we added primes to be true. We already are using longs. And let's see here. We need to recalculate where we're putting these in the array and how we're getting them out. So so right here we need to say, okay, int p, I'm going to say the p equals I 2 times I plus 3. That's just this. Oh, that was an ugly Sharpie draw. We already did this. Equals 2 times I plus 3. And because I'm paranoid, I'm going to add these guys. And then I want to make sure this is an int. Okay. So instead of this, actually we'll calculate this in here. And instead also, because we're going through this mini array, we're not starting from 2 anymore. That doesn't mean anything. So we're going from 2 to size. We calculate p, which is what the value we're actually looking at is. Results, we add p. And then as we're searching through, we need to recompute this. So really it's going to be 2 times this. 2 times I. Let's see. So we have, what do we have? We had 2I plus 3. So if I squared was in there, it would be 2I squared. plus 3. I think there's another thing we're missing here. My notes say it needs to be 2 times I squared plus 6 times I plus 3. And if we I plus 1, I don't know. I think we're trying, so here, I think we're trying to translate this P back into I space while also starting the search from I squared. So I think that's what this piece is doing. And then we're not going to go to N anymore, we're going to size. Sorry about that. This is not the best. When we increase through the array though, we're going to increase by P. And then that remains the same. And there are bugs. I found this with the official solution. It has to do with line 22, not computing the size correctly. There appears to be a bug there, but if you got this far in an interview, and you would not be compiling this. This all be on the whiteboard. The main ideas are get the brute force solution, get the sieve idea, and if you can get the divided by 2 space optimization and the different optimizations with where you can search from when you're sieving, your interviewer should be happy with that. So that was Prime Sieve.